My name is Sarahmay Schlea, and today I'm going to talk to you about prototyping an experimental early warning system for rainfall-induced landslides in Indonesia using remote sensing and geospatial datasets. Ironically, I'm recording this during a thunderstorm. The objective of this paper was to provide a new, more well-developed disaster early warning system for landslides, specifically landslides induced by rainfall. This is needed for disaster preparedness and hazard management. The prototype was taken from an empirical system and was improved upon to become a more physically based landslide prediction model, which uses satellite remote sensing platforms. This prototyped early warning system integrates three things: susceptibility mapping and hotspot identification based on the land surface, satellite-based precipitation monitoring systems and precipitation forecasting, and a physically based rainfall-induced landslide prediction model, also known as SLIDE. Next, I'm going to talk about the parameters for data collection. In order for the SLIDE model to accurately predict landslide susceptibility, a number of factors needed to be taken into consideration. First, elevation data needed to be obtained, in which 30-meter DEM data was acquired from the Advanced Spaceborne Thermal Emission and Reflection Radiometer Global DEM, also known as ASTER. Next, soil parameters needed to be defined. This information came from the Food and Agriculture Organization of the United Nations, using a moderate resolution imaging spectroradiometer land classification map, and soil depth was assumed to be 2 meters for accuracy. Rainfall data needed to be examined as it was a dynamic trigger for landslides. This data was sourced from NASA's Tropical Rainfall Measuring Mission, also known as TRMM, which provides real-time precipitation values. It was also taken from the Weather Research Forecasting Model forecasts, also known as WRF, which is a rainfall prediction model. When looking at the SLIDE model, we know that it has been modified from two different studies. The first was Fredland in 1996, and the second was Montracio and Valentino from 2008. The SLIDE model is a mathematical model that translates the physical phenomenon of the rainfall triggering process through differential equations. The SLIDE model highlights destabilizing forces due to water downflow and the contribution of partial soil saturation. The mathematical formulation is the link between rainfall amounts and the Fs expression, which is the ratio of resisting forces to destabilizing forces on a soil slope. Where Fs equals 1, a slope has begun to slip. The smaller the ratio, the less stable the slope. The study focused mainly on Java Island in Indonesia from December 24, 2007 to January 2, 2008. Since Indonesia falls within the tropics, it experiences a lot of rain. Frequently, Indonesia suffers from typhoons, landslides, and typhoon-triggered floods. From 1981 to 2007, the landslide frequency in Indonesia had increased to 49 events per year. This map shows the entire study area of Indonesia with a focus on Java Island. It also shows the landslide occurrence versus elevation. Here's another map of specifically Java Island in Indonesia that shows landslide susceptibility versus the degree of soil slope, where red is very high and green is very low. From this paper, we learned that the SLIDE model provides a weighted hazard rating for mapping landslides. This integrates both GIS and remote sensing techniques. From this model, the researchers were able to classify landslide susceptibility into 5 different categories, as was seen in the last slide, with 1 being very low, or green, and 5 being very high, or red. When FS values were calculated with a susceptibility of 4 and 5, it was observed that 1.76% of land area fell within susceptibility category 4, and 13.61% within susceptibility category 5. But during peak typhoon rainfall, 25.06% of land area with susceptibilities of 4 and 5 had FS values of 1.2, in which FS values below 1 are usually predicted to have landslides. By using the WRF and NASA's TRMM data, landslides from the December 26, 2007 typhoon can be simulated, in which warnings would be issued when FS values fall below 1. The researchers concluded that water content in the soil column during a rainfall event is an important factor in determining slope stability. It was also determined that the slide model actively integrates into an early warning system by linking water content in the soil within the rainfall series. Not to mention, it aims to predict regional landslides by mapping FS values over a region in which 30-meter DEM data had been mapped. Remember, the FS values are equal to the ratio of resisting forces over destabilizing forces on a soil slope. From this, we saw that the slide model had successfully predicted the occurrence of 2 landslides on the dates of real events. While this model and early warning system would be a great tool for predicting landslides all over the world, the researchers realized they had neglected important factors. These include the soil strength between different soil layers, as well as geologic structures that can potentially accelerate slope failure. The researchers also realized that the model would be more successful if certain observed landslide information could be available. This information consists of the time of failure, as well as the total area and volume of failure colluvium. There have been limitations with using the early warning system, such as it is typical that FS values dipping below 1 don't always generate landslide conditions, and the system has only been validated for small, localized events. The researchers realized that the resolution and absence of certain surface inputs can vary, creating inconsistency, and the quality of soil data can limit soil stability calculations.